So next is claim 2, where we start with a large S and we have to find k points or k vertices such that starting from this S, everything is a neighbor. Now since we don't have any information about S, we cannot do this, we cannot construct U systematically. So what we do is we give a probabilistic argument. Since we don't have extra information about S, or inside S, we only know the size, we don't know the exact elements, right? We try to construct U by a probabilistic argument. Okay, so this will be an interesting proof with probability. So how do you use size of S, right? That's the point of this. So choose U1 to UK randomly. Okay, so instead of trying to construct them or design them, you just pick them randomly. And let us now calculate gamma US. Does it work? So we'll basically calculate the probability that gamma US is everything. So let ER be the event that an element R is not in gamma US, and let ERI be the event that R is not a neighbor of S because via UI. So R is not in S plus UI. S plus UI is every element in S you are adding, you are XORing with UI bitwise. Okay, so basically we are interested in the probability of this bad event, that a point vertex R is not a neighbor of S. So let's estimate their probabilities. So what are their probabilities? So probability of the event ERI over this random U. So if you pick U1 to UK randomly, what is the chance that R is not a neighbor of S via UI? So this is 1 minus R plus S, the size of that, by 2 raised to m, which is the size of whole space. Right, why is that? So R plus S are these good strings, and UI is not one of them. So these are actually the U's that work. These are the UIs such that UI is in R plus S. And since ERI is the event that UI is not in R plus S, we subtract that out, and then what you get is so this is equal to 1 minus size of S divided by 2 raised to m. And what is size of S? In claim 2, size of S is size of S by 2 raised to m is more than 1 minus 2 raised to minus n. So this is less than equal to 2 raised to minus n. Okay. So which is a very small probability. This event happens with a very small probability, which means that if you now look at probability of the event ER, so ER is the event that R is not a neighbor of S by any of these UIs, right? So you have to go over U1, U2, UK. So that's product of probabilities. And each of these probabilities is 2 raised to minus n. So you get 2 raised to minus kn. And the way we have defined k, we for this reason we defined k to be m by n. So what you will get here is 2 raised to minus m. Okay, so the event ER happens with probability smaller than 2 raised to minus m, which means that the probability when you randomly pick U that there is an R, there is an R for which ER happens. This is, and where is this R? This R is in the space 0, 1 to the m, right? So this is 0, 1, the size of this space times the probability, which is 2 raised to minus m, which is just 1. This is by the union bound. So hence the probability that there is some string outside gamma US for random use, it's actually less than 1. That's the probability, which means that the probability over random U says that all the R's ER doesn't happen. Okay, this is positive, which means that there exists a subset U such that gamma US is everything. Okay, so by showing probability positive, we have shown the existence of U such that every R is in the neighborhood of gamma US. Okay, so this finishes the proof of claim 2. And once we have both these claims, we are almost done, because What do these claims tell you? So claims 1 and 2 imply that for all x input strings, x is in L if and only if there exist u1 to uk such that for all r there exists basically this set U with k vertices, k points, such that for all R, one of these R XOR UI is true, right, for some I. So there exists a set U such that no matter which R you take, so this domain is 0 1 to the m. So from this domain there will be these, no matter what u1 to uk, choice of u1 to uk such that no matter what R you pick, one of these strings R XOR UI for one of these UIs will be a good string for the yes input string x, right. This is because this R plus UI that we picked, it's in S. Because R plus UI is in S for some I. There exists an I such that R plus UI is in S. It's equivalent to saying that gamma U S via UI, there is a neighbor, R is a neighbor via UI of some point in S. Okay, so that is for the yes string x. For the no string x, the set S will be so small that no matter what u1 to uk you pick, this statement will not be true. Okay, simply because gamma us is not everything. So that is what claims 1 and 2 have shown, which is nothing but showing that L is in sigma 2. Right. So L is in sigma 2, which means that BPP is in the intersection. Okay, so that finishes Sipser-Gach's theorem. And although we don't know BPP in NP, this is still a good amount of information, because it's telling you that BPP is in NP to the NP and it's co. And what it also tells you is the following. So this in particular means that if BPP has an NP hard problem, then what will happen? Yeah, let me not get into this. Let me just ask this as a question. So could BPP have an NP hard problem? Okay, what will happen if BPP has an NP hard problem? Does this result give you anything, any indication? So practical implication will be huge, because it would mean that you can in particular solve SAT by a randomized polynomial time algorithm, right? And So that will already solve all these hard optimization problems in practice. And to formalize those connections, let us move to randomized reductions formally. So randomized reductions to NP, which is to SAT, and also log space. Recall that you have seen this while we were finishing Toda's theorem. So there SAT was randomized reduced to parity SAT. And we can now take that concept, we can formalize it more generally, since we have seen probabilistic Turing machines now. So language A reduces to B in randomized polynomial time. We'll denote it like A less than equal to R subscript sub R B, to mean that it's a randomized polynomial time reduction, not a deterministic polynomial time one. If there exists a polytime probabilistic Turing machine M such that for all input x, probability of so M will transform the input x to something else, M of x, and this will be given to B. And we want this to be equal to A of x. So the chance that this happens will be quite good. Okay, and here probability is over random bits of M. So this is a new notion of reduction. Okay, A reducing to B via a probabilistic transformation M, which is a polynomial time probabilistic Turing machine, and with good chance x will be mapped to correct M of x. Okay, such that A gets solved by B. So as I said, you can recall here what we did. With polynomial hierarchy, so we showed that every problem in polynomial hierarchy actually reduces to parity P. Right, that is what we had shown, and now we can define. This helps us to define BP as an operator on complexity classes. So we can define a randomized version of NP now. We'll call it BP.NP. So BP.NP is defined to be the set of those problems that reduce to SAT. In randomized polynomial time. Okay, so if it was a deterministic polynomial time reduction, then this is exactly the class NP. All problems in NP reduce to SAT, but we have now allowed the transformation to be randomized. So we are not very sure whether we have gone above NP or we are still in NP. Okay, but this is a way to define new classes by randomization. So in general, we can define for any complexity class BP.C to be the set of those languages that reduce to C. Okay. So BP is a new operator, and of course it's an open question whether BP.NP is NP. Okay, NP is clearly contained in BP.NP because you can just ignore the random bits, random choices, but we don't know whether it's bigger or exactly equal. We conjecture it to be we conjecture it to be equal. We conjecture them to be equal, but nobody knows for sure. Some easy properties now. So NP, as I just said, is a subset of BP.NP, and when you do co of this, what happens? So by via this randomized reduction, you can check that this is the same as BP.CoNP. Okay, so this co and BP you can interchange. Okay, so co of BP.NP is the same as BP.CoNP. So this you can think of as the randomized version of CoNP. And just like BP acting on these general complexity classes, we can also define it for space bounded classes. So, or for small classes, we have to change polynomial time to log space. For smaller complexity classes, we can use log space. Variant of reductions. So you get BPL. So L is in BPL if there exists a log n space probabilistic Turing machine M such that for all input strings x, probability that M correctly computes L for this input, this is quite high, more than 2/3, and random bits of M. That's the probability. Probability is over the random choices that M made. Okay, so M, this is just saying that a probabilistic Turing machine in log space work tape of size order log n, where n is the input size, it is able to solve L with high confidence. Okay, this is 2/3, which can be amplified to close to 1. And so this is just log space reduction. Based on this, we can now also define classes. I mean, using this reduction, we can define classes. So let us do that. New class is RL. Yeah, let me take that back. We can use log space restriction on work tape. So we are actually defining log space computation. So instead of L, we have defined BPL. I mean, we have kind of expanded L to BPL by using this probabilistic Turing machine, and we can expand L in a different way, which is one-sided error instead of this two-sided. So that's RL. So L is in RL if again there exists an order log n space probabilistic Turing machine M such that for all input x is in L if and only if x is a yes string, if and only if sorry, there will be two conditions. For the yes strings, error is allowed. But not more than error cannot be more than 1/3. Error up to 1/3 is allowed. For the no strings, no error is allowed. So for no string, you cannot get 1. You will get 0. Okay, M will always reject. So if this happens, then we say that problem is in RL. This is the one-sided error case. So RL is one-sided error, while BPL is two-sided. Okay, like we did for BPP and RP, similar definition.